Well, we are going to start. Welcome to the seminar with IT Pioneers and Leaders 2022 edition. Today we have as our special guest, Jeffrey Ullman. Acknowledgement. We would like to thank Dr. Jeffrey Ullman for accepting our invitation, Dr. Manuel Certuche, Dean of the School of Engineering, dear Joaquín Acevedo, Dean of the School of Engineering in North Region, dear Alfredo Galván, Director of the School of Engineering, Engineer Luis Ricardo Salgado, Director of the Computer Department, Engineer Rafael Dávalos, Director of the Computer Engineering Track. Jeffrey Ullman is a computer scientist and Stanford W. Askerman, Professor Emeritus at Stanford University, distinguished author for the textbook and compilers commonly called the Draw Book, Theory Computation, Data Structures, and Databases. Ullman's honors include receiving the 2020 ACM Turing Award with Alfred Aho, the IEEE John von Neumann Medal, and the Donald E. Knuth Prize.
We appreciate your time and effort to be with us. Welcome, Dr. Jeffrey Ullman.
Okay, hi. Well, thanks very much for inviting me. I'm going to talk a little bit about mainly about data science and machine learning, and I guess, well, my personal take on it. And so with that, I'm just going to share my screen and present some slides. Let's see. So how are we going to do it here? Yeah. You can see I was playing solitaire while I was waiting for them. Okay. Come on. There. Okay. So what I want to talk about, I mean, some of the hottest topics in computer science these days are what's called data science, artificial intelligence, and especially machine learning. I think everybody wants to do machine learning these days. So what I want to do is sort of start from the highest level of computer science as a whole, and then talk about how things like data science and machine learning fit into it. And I want to close my talk with an example that's very fun to me. I'm very fond of, called locality sensitive hashing. What it's an example of is what I think is a very interesting data science-y algorithm that is not, it has nothing to do with machine learning. At any rate, very commonly computer science is divided into hardware and software. I'm going to talk really about the software branch, but just to say something about hardware, which of course is very, very important. I don't want to minimize it. One of the interesting things is that if you go back 20 or even maybe 10 years, the assumption was that all you really need to know about hardware is the Intel, the x86 architecture, because all machines were using that, even if they weren't made by Intel. Today, there's a lot going on in hardware that is fairly modern. Well, the graphics processing unit, or GPU, is one of these things that's I think pretty well known, but more recently, Google has come out with what they call the tensor processing unit, which is a more powerful kind of a chip for doing some very specialized things. Really, it's a matrix multiplication chip. Very important in machine learning, by the way. The FPGA, a field programmable gate array, is another thing. You can do a lot with that. Well, as I said, it's programmable. And the interesting thing is there are actually hundreds of companies now. I've heard 200 different companies developing different chips, each of which plays a role in common computations, typically machine learning kinds of computations. Okay. Another interesting fact is that apparently the speed of networking hardware is growing faster than the speed of processors, which is hardly growing at all. One consequence is that supercomputers have sort of become computer clusters, like the cloud computing clusters that you'd find from Amazon or Microsoft or Google. Essentially, supercomputers now are computer clusters. Well, going back to the software branch, you normally divide software into really two parts as well. One is systems and the other is applications. Now, I'm going to talk mostly about the applications branch, but there are still, of course, many interesting things going on in systems. So, for example, computer security and cryptography is a very important mathematical part of computer security, but it's certainly not the whole thing. Obviously, networking, cloud computing are becoming very important. One of the things which I don't know, I maybe because I'm getting rather old these days, is I've come to see how important human-computer interaction is. I used to sneer at it because, frankly, the field is not one that has a lot of mathematical rigor to it. It's more a design issue, but it's become very important as people are dependent upon computers. There are so many things these days where you really you have to access it through a cell phone app or something like that. If you don't understand how this app works or how to make best use of it, you've lost an ability you used to have when you were able to talk to a person who might help you out to, I don't know, well, you bought a hammer and you discovered that the hammer it doesn't work properly and you want to exchange it. You used to be able to call up somebody and make the arrangements. Now you have to do this all online. And it's the job of computer scientists to make it so that people with limited sophistication, let's say, such as myself, can navigate a system that they've never used before. And anyway, that's my personal opinion. Okay, so now let's talk about applications. Again, this is where I'm going to be focusing on for the rest of the talk. First of all, there's an old view again, that it was all about inventing algorithms, and certainly there are some very many interesting algorithms that have been invented and are in use. Well, more recently, people have come to realize that applications are built not only from algorithms, but from data and how the data is managed. And in particular, that machine learning is central. Machine learning, after all, is really building an application from the data rather than the algorithm. And if it's not obvious, there are lots of career opportunities. Many of these, many careers and applications are for people who know not only computing, but who know some other application, biology, medicine, commerce, but something other than just programming. Okay, so here's, I guess, as far as I want to go with the diagram. Applications, again, I see a lot of applications as artificial intelligence or AI applications. Others are what I think is commonly called data science application. And there are lots of others. I'm going to talk about, again, this one example of an interesting algorithm that sort of is outside the AI data science field. And machine learning, again, is a body of techniques that are useful in both AI and data science. Okay, and I think it's important to remember that structure. The AI, data science, machine learning, they're all different. And machine learning is, at some sense, a lower level. It's a tool that are used to solve problems in AI and problems in data science. Okay, so let's talk a little bit about artificial intelligence. First of all, again, 10 or 20 years ago, the assumption was that the job of artificial intelligence research was to learn how to better simulate human thought and human reasoning. And I think that's not really the case. Artificial intelligence became important when people realized that it was really just about solving certain kinds of complex problems, and that there are many algorithmic tools that artificial intelligence uses. Machine learning, obviously, is one of them. Okay. So I just want to give you, an example of how I think AI has changed. Okay, for example, driverless cars, right? A car that can drive itself is obviously a human-like task, and the old approach would be we have to simulate how a human approaches driving. So you might, one common approach would be what they called expert systems. So you throw, large numbers of rules, and the decisions made by the car would be made by following these logical rules. Let's give you an example here. It's maybe kind of silly, but okay. Some expert would have to enter a rule that says, if you see somebody crossing the street in front of you, stop the car, right? It's one of the first things you learn when you are taught to drive, right? So that kind of makes sense, but it doesn't work. One of the reasons it doesn't work is you need so many rules that there's no way to tell how they interact, something will go wrong because of an unanticipated consequence of the many rules that different people have thrown in. Each person not even knowing what rules the other people have proposed. Well, in fact, the way driverless cars are being developed now is you send the cars around, and the cars have many sensors. They essentially see what's going on, and this is all recorded. This becomes data, and the data is then used to build, using some machine learning algorithm, something that will will basically make the judgments for the car as to what to do. And the fact is that while these driverless cars are not perfect, they're better than a typical human driver already, and will probably get better as they have more data to learn from. Okay, so let's talk a little bit about machine learning. Again, if you go back a generation, the idea was people would build software that would sort of observe what it was doing, and when it made a mistake, would learn from that mistake, and the software would modify itself and presumably do better. I mean, that's an interesting idea, but it turns out, again, not to be nearly as useful as what machine learning has become. And so the new view of machine learning is that it is simply about the development of models and a model is really a program that makes decisions. And it does so from large amounts of data, this data is called the training set. So in some sense, you're teaching the program to do what the training set tells it to do. Okay, but I'll give you an example in a moment. The software itself isn't learning from its own experience, but rather from the data that you give it. So let's talk. A common example of machine learning is email spam filters. So when my Gmail actually puts about 300 emails a day into my spam folder. I never see them. How does Gmail do that? Well, they ask you to flag an email if it's spam, and then it assumes that messages that are not flagged are not spam. Gmail, I'm just using Gmail as an example of a large-scale mail system. It gets a training set every day of labeled examples. You have lots of examples of spam emails and even more examples of non-spam emails. And on a daily basis, maybe even more frequently, I don't know, they train a neural net, machine learning algorithm to decide, is a given email a spam or not. And I want to just emphasize that the software isn't learning. They're using different training sets each day. The reason you want to do that is because the spams that you'll see tomorrow will probably be different from the spams you see today. So they have to keep using new training sets, but the software itself is the same software. It's just getting different data to learn from. Okay, just to give you an example, a simple model and this would be, because really simple, would be to examine the spam emails and the non-spam emails and find words that appear much more commonly in the spam emails than in the non-spam. So for example, again, this is probably a little out of date, but there used to be spam emails that would claim to be a Nigerian prince with money that they're willing to share with you if you send them $1,000, let's say, for their airfare. Of course, they keep the $1,000, they never share. There's nothing to share with you. But you can imagine that the spam filter might learn that emails from people claiming to be Nigerian princes are very likely to be spam. Okay. Well, as should be obvious, the actual model that a system like Gmail uses is way more complex than this. Okay. Well, there's, I think, a common misperception is that the terms like artificial intelligence or data science and machine learning are really referring to the same thing, and I don't agree with that, and I want to try to to separate the concept. First of all, again, machine learning is simply a body of techniques for building models. It's algorithms. Okay. Artificial intelligence is really the development of software that solves a certain class of problems. And I would put in that class of problems what I might think of as computer science problems. That is, problems that are so general that they would be used in many different kinds of applications. For example, language translation. Almost any kind of application these days could use good language translation. Chatbots is another example. You've probably found that there are many, let's say, websites that will try to engage with you to learn your problem. And again, so if you say, I bought this hammer and it doesn't work and I want to return it, the software behind that, they call the chatbot, that is trying to figure out what your problem is. And having said, probably the fact that it's a hammer is probably not relevant. The fact that you want to return it is, so it might send you a form to fill out to return an item or something like that. If it's doing a good job, these things are actually very complex. Think about, for example, people are developing chatbots that diagnose medical conditions. Very, very complicated. In networking, discovering intrusion detections, that is detecting intrusion, sorry. A very interesting problem. How do you tell whether a combination of packets being sent over the internet, let's say, is really a denial of service attack? Anyway, there are lots of these general core problems. Okay, to me at least, I said data science is using many of these same techniques, but the purpose is to create specific applications to a specific science or industry. For example, algorithms to decide what ad to show you when let's say you go to Amazon to try to buy something, or algorithms, let's say science of astrophysics, detecting gravitational waves. The algorithms to do that are, of course, very, very very complex, very interesting. But the purpose then is not general. It's to answer a specific question in astrophysics. Okay, well, again, there's no question that machine learning has grabbed people's attention to such an extent that often people don't see really bother seeing a difference between machine learning and data science, or machine learning and artificial intelligence, or all three. I want to give you really three reasons why I think that machine learning is not everything. Well, first of all, machine learning tends to claim too much. Some examples here. For example, clustering, that is taking, dividing sets of points into a small number of clusters or sets of nearby points. People were doing that long before there was a machine learning as a popular thing. Gradient descent. Well, it's really, I mean, Newton was talking about this in the 17th century. Come on. Association rules is again something I'm going to talk about that in a second, but this was an idea that really came out of the database community. The second concern is that there are problems in computing and development of applications as AI or data science does, that cannot really be characterized as the search for a model. And again, I'll give you at the end an example of locality sensitive hashing, which is really not, has nothing to do with models in the machine learning sense. And the third problem is that sometimes understandability counts, and it's a sad fact, perhaps, that the most powerful machine learning algorithms are also the least understandable. So let's talk about association rules. These are rules discovered from data about what we'll call items that cause effects, often the buying of another item. The original application was looking at what are called market baskets. That is, when you go to a supermarket, you buy several, some set of items, you put that in a market basket, and when you check out, the cash register knows that you bought these items together. So you can go through the data that's accumulated by the cash registers and discover things like people who have bread in their basket are more likely to also have butter than random people are. So the store owner could perhaps run a sale on bread and increase the price of butter so that they'll make the money back and bring in more people who buy bread. And then while they're there, they also buy the butter at a higher price. Little tricks like that. Well, this came out of the database, in particular, Rakesh Agrawal at IBM and a number of his colleagues developed both the idea and an efficient algorithm for going through the data and discovering the most common association rules. Let me just give you a quick example in practice. This, of course, has nothing to do with shopping and market baskets in that sense, but you could think of the items as words, and the baskets are emails, and each email is a basket of words. It contains some set of words. Now you go through that data. Let's say if you went through the data of known spam emails, you might discover a rule like if an email contains both the words Nigerian and Prince, then it's likely to be a phishing email. Now, I should tell you that this is by several percentage points less accurate, this approach, than even a very simple machine learning model, let alone the very powerful machine learning models that let's say a system like Gmail would use. An example of a machine learning model might be to go through the data, learn the best weight, which might be positive or negative, on each word, sum up the weights of the words in the email, and say it's phishing if the sum of the weights exceeds a particular some threshold, which you would also learn. Trouble is, okay, association rules are simple enough to be understandable. That is, if you actually, I mean, obviously you're not, but if you were a Nigerian prince and you could ask the system, why are you always treating my emails as spam? Well, they say, well, here's a rule. See, it says if you say you're a Nigerian prince, then we think you're spam. Okay. Again, you may not like it, but at least you can understand it. Now, you can every time Gmail puts something in spam, you can click a button and ask it why it regarded it as spam. Now, sometimes it has an actual reason, but the typical answer is, it says, it looks like other emails that people said were spam. So what does that mean? It means, we have this mysterious model of spam, and we learned it from what people said was spam, and I can't explain to you what that model is doing, but it said it said this is a spam, and that's all you can tell. Now, again, that's not a big deal. I mean, Google does do pretty well in identifying spam. The trouble is, you have situations like insurance companies. They try to figure out who's likely to have an automobile. Let's say if it's automobile insurance, they're going to try to figure out how likely are you to have an automobile accident, and they're going to use the data of, historically, where have accidents occurred and who has been involved in them and so on. And they'll build some model, and the model may be incredibly complex. And the model says you have to pay more for your insurance because somehow the model has decided you are a likely automobile accident waiting to happen. But it can't explain it to you. And that's frustrating enough that one could even argue that it's just an inappropriate use of machine learning. Well, with that, I want to just close with this example of, again, an algorithm that is useful in many kinds of applications, including AI and data science applications. It's called locality sensitive hashing. It's in no sense involves a model, but yet I think it's a very interesting algorithm. At this point, I'm going to recommend a book that I wrote with my colleagues, Yuri Leskovich and Anand Rajaraman. I don't feel guilty about plugging it because it's free. It's published by Cambridge University Press, but they let us offer a free download, and here's you can see the URL there. Okay, And it talks about, it's really about data science, the algorithms for data science. It does talk about machine learning, but also many other kinds of algorithms. So the problem of locality sensitive hashing is if you're given a large set of items and you have some notion of similarity, and I'll give you an example of that. You want to find the pairs of items that are similar without looking at all the pairs of items. The problem, well, if I have even 1 million items, you have about 500 billion pairs of items. Looking at 500 billion pairs is not reasonable. Even 1 million items is a tiny number compared, let's say, with credit rating agencies receive hundreds of millions of records per day of financial transactions, and they want to group them by who's the individual that this is a record about. So they have to, if they had to look at all pairs of items to see whether they refer to the same person, it would just be completely beyond what computing could do. Anyway, locality sensitive hashing, in some sense, there's some magic to it in that you can find the similar pairs without looking at all the pairs, and in fact, not looking at most of the pairs that are not similar, although you have to look at some. So the application I want to talk about is entity resolution, and it has, again, formally the idea is you're given a set of records, and these records have fields, which typically will have value. Some fields might be missing in some records. And the fields sort of tell about people. So the field might have a name. There might be a name. Sorry, the record might have a name field. That would be very common. Might have your phone number, your address, that kinds of things. And you want to find the records that refer to the same person. Now, it's hard to do without comparing records, because just because the names of the name fields are different doesn't mean that it's not that it's not the same person. For example, your name might be misspelled in one of the records, or if you have a middle name, one record might have the middle name, another record might have only the initial, another might not have anything for the middle name at all. I think the Spanish style of names are especially tricky. I looked actually recently at a data set of records from Colombia, and you have people, it's the same person. We know it's the same person because there was a government issued ID associated with them. Could have between 2 and 5 different elements. Okay, so it's kind of tricky. And as I said, 1 million records. If you have 1 million records, the number of pairs of 1 million records is 1 million choose 2, which is about just a little bit under 500 billion records. Now, these days, even though you can sort of do 500 billion things with a powerful enough computer, but when you start talking about hundreds of millions of things, which, as I said, is common, at least in the world of credit rating agencies, the number of pairs of records is just so astronomical that there's no way you're going to look at them all. Well, again, the locality sensitive hashing trick lets you avoid looking at all pairs, and in fact, you don't look at that. You look at very few pairs, very small fraction of the actual pairs, but you have to accept a few false negatives. That is, records that do refer to the same person, but yet you never look at that pair, and therefore you never merge them. And the key, again, I'm going to assume that everybody is familiar with the idea of hashing, where you have some functions that throw items into buckets and distributes them pretty randomly into buckets. Well, what locality-sensitive hashing does is it requires not a random hash function, but one that's carefully designed to have the property that if the items are similar, then there's a good chance they're going to wind up in the same bucket. And if they're not similar, then there's a very poor chance that they'll wind up in the same bucket. Now, again, this may sound like magic, because you have to have an awfully smart hash function to be able to look at an item and tell what it's similar to. Anyway, we'll use several hash functions. In my example, I'm going to use 2, but you might use 100 or something. And the idea is you will only compare the items that wind up in the same bucket for at least one of those hashings. And again, that should guarantee you that, okay, that similar items will, if they don't wind up in the same bucket for one hash function, there's a good chance they will for some other one. But the buckets will still tend to consist mostly of records that do represent the same person. So one thing I'm going to build a hash function that throws the records into bucket. Each bucket is associated with a particular name. So records wind up in the same bucket if and only if they have identical name values. Now, if 2 records do have identical name values, there's a good chance that they refer to the same person, but there are people that have exactly the same name. Okay, so the bucket's going to have records from people that that have the same name but are different people. Now, you're going to still have to then look at all those pairs and say, well, are these really the same person, or are they the same? Well, maybe they may have the same name, but their phone numbers are completely different, and they live in different cities, and so they're probably not the same person. So we might have another hash function that puts people in the same bucket only when they have the same phone number. Well, again, if 2 records referring to the same person are likely to have the same phone values, but there are typos. So someone might have a phone number that differs from yours by a single in a single digit, and someone misentered that phone number and it came out as yours, or roommates might share a phone, and so they use the same phone in their records, but they're really different people. Same thing with address. If people live in 2 records referring to people living in the same address, very likely are the same, but again, roommates would have the same address. You may be renting an apartment now, but someone else rented that same apartment last year, and they used that address in an old record, and so the records have the same address, but they're different people. And so there might be more fields that the records have, and and that sort of have this property that if it's the same, it's likely that that you're talking about the same person, but not guaranteed. Okay, so again, what you want to hope is that if two records that really do represent the same person, they will, even if they don't have the same name, they'll maybe have the same phone number, the same address, and so they'll at least wind up in a bucket together, and you'll look at the question: are these records representing the same person? But again, just to remind you something that's important is just because two records wind up in the same bucket doesn't mean that they necessarily refer to the same person. They're just candidates. They're a pair that you need to look at. Okay? But then for many different reasons, you can have records in the same bucket that once you look at that pair, you realize they're not really the same person. Okay. So just to summarize, we'll use fields like a name and phone to do several different hashings of the records. We will compare records if and only if they appear together in the bucket at least once. And you hope, as should be the case, I've actually done this experiment. The chances that records will appear together in a bucket, it's a very small fraction of all the records, of all the pairs that do appear in a bucket. But again, unfortunately, you can have records that represent the same person, but for various reasons, none of the fields you use to hash on do you have identical values. Okay. And okay, so with that, I will stop, and I'm happy to, I guess, answer questions.
Well, now we will start the Q&A, so please raise your hand with some questions.
Okay.
Okay. Okay. Please, Rafael Dávalos.
Thank you, Dr. Jeffrey Ullman. Regarding to your compiler books, how many computer languages do you remember being a consequence of your books?
Wait.
A language created by an initiative of your books of compilers, about compilers.
Oh, okay. Well, the answer is either 0 or so many that I couldn't possibly count them. And it depends on what you consider a language. Was C++ invented because of our books? No. Was Python invented because of our books? No. But one of the things which I think our books tried to show was that there are tools for building what Alejo always refers to as little languages, where you design a special purpose, really notation for describing some simple task, and then you can very quickly, using the tools we've developed like Lex, and that we talked about in the books, things like Lex and Yak, that let you very quickly parse an input. Al, in fact, for example, things like EQN. This was an early. You now find it as part of TeX. but it was a little language developed by Brian Kernahan for what it did. It was just for typesetting equations. And there's mathematical equations, and so it was a notation for describing equations, like if you want x with subscript 1, you would write x space sub space 1. Now in tech, of course, it was just space underscore 1. Sorry, x underscore 1. But same idea. So it's not EQN is not a programming language of any sort, in any sense, but it was something that did profit from the kinds of technologies that were described in the book. And as I said, there are, I believe, at least thousands, if not millions, of projects that have used tools like Lex and Yak to basically just build front ends for some interesting notation, like arithmetic expressions, and then compiled them into something else, like the bitmaps that are necessary to typeset, or okay. Anyway, that's.
Okay, now Daniel Grajales.
Hi, doctor. Thank you very much for your presentation. I have a couple of questions. At the beginning of the talk, you were talking about the hardware part and the big variety that we have nowadays. I wanted to ask your perspective in terms of the photonic chips. There are some sorts of photonic integrated chips, even some processors at some point.
Yeah.
And on the other hand, if they keep developing, what would you imagine that would be a new compiler language for them, or would we adapt anything?
Okay, well, it's again, I don't really know much about photonic chip development. My understanding is that the idea is that you can send signals very rapidly from one part of a chip to another. I think it's a good question. I'm not sure that the standard logic design languages wouldn't be appropriate. Obviously, the compilation becomes more interesting. That is, you would need to take the logic and compile it into the chip in a different way. Obviously, one that took advantage of the capability of the photonic messages. It could be very interesting to sort of to identify in the logic what is there that will take advantage of the photonic capabilities. But I honestly don't know enough about it to say whether that's a good direction to think about or not. Could be.
Okay, thanks. Now, Jesus Guillermo Falcón, please.
Oh, okay. First of all, thank you very much for your presentation, Professor Ullman. It was a pleasure for me. Can you hear me?
I can indeed, yes.
Okay, thank you very much. It was a pleasure for me to hear you because I have all your books. But my question is, it's kind of out of the context of the presentation, but I would like to know what will be your the way to have a successful career in computer science? The question is because I'm a young researcher, so I would like to know what's the tip for having the key point to have a successful career in computer science.
Oh, well, look, first of all, there are many roads. Even if you restrict yourself to a research career, there are lots of people who are very successful and don't do research at all. They just deploy good stuff. And that's probably the vast majority. For a young researcher starting out today, life is a lot tougher than it was when I was starting out. This is there were very few of us. We didn't know much, so anything was new. I would, but on the other hand, it's become so obvious that computing, the knowledge that a computer scientist brings to problems has become so important in so many different fields that that there are tremendous opportunities. I would give you one. I guess the most important thing is to approach your research not from the point of view of what are people doing research about. That is, the mistake that most people make is you'll go to some journal, you'll read a paper, and the paper will do blah, 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 and then at the end there's an open problem. You say, oh, I can solve that open problem. Okay. And maybe you solve the open problem, and then you write, or you solve part of the open problem, and then you write a paper. And at the end of that, you say, well, and here's the open problems I see. And then somebody will pick that up and do that. And what happens is the only motivation for writing these papers is because some other paper said to write it. And I think that's exactly the wrong way to proceed. The right way to proceed is to ask yourself, what do people need and don't have? And now that, of course, is a very, very hard question. It's always easier to see at the end that, gee, we really did need cell phones, but, but to see, in advance, gee, if people had this little, this little thing that they could hold in their hand that they could make phone calls with and take pictures of everything and do the, handle their email and so on, that they would really be carrying that around in their pocket. That's really hard. Okay, but I mean, once you see that people could use that and actually need it, there are a million problems to work on, but you'd probably be smart enough to solve many of those problems once you realize that that it's really in the critical path. One way, of course, to be exposed to problems that people really want solved is to be working with people in an application. And I don't care whether it's you go to work for Amazon and they're trying to figure out how to sell more stuff, or you go to work in a hospital and you see how they're trying to diagnose patients and read these CT scans and so on, and just make more accurate diagnoses. But again, the thing that I encourage everyone to think about, no matter whether you want to be a researcher or a program managers, and start from what do people need, not what have people who write papers been doing, or have been writing papers about.
Thank you very much.
Thank you. Well, now with Victor Manuel Rodriguez.
Hi, thank you so much, Professor. Talking that part of the same question, today in the industry, we have the problem of the hardware industry generates new CPUs that generates that with instructions for machine learning or data science on one side. So x86 platform is coming with specific instructions for machine learning, data science, and so on. On the other side, the applications have the issue of having the library, the compiler does not detect the part of the algorithm that it's going to use that instruction. How do you see in the short and long future that problem could be solved? Because it's quite an issue. We have in part the instruction in the hardware and the algorithms that we write, let's say in C, C++, or any other language, if we compile with traditional compiler, they don't detect to use that instruction properly.
Yeah, I mean that's one of the great problems in computer science, right? Yeah, every time the platform changes, the compiler has to change. Again, my preferred approach would be, again, sort of it's this little language approach. Instead of, saying, gee, I want to take the world's entire code base and recompile it so it takes advantage of some instruction that has been put there to do matrix multiplication or something very specific. I would rather say, all right, write a little language that lets you describe operations in linear algebra and compile that. Okay. Just rethink that and recompile it to take advantage of the new capabilities of the chip. What's I think even especially interesting is is taking some of these new what they call accelerator chips, which are not general purpose computers, but are designed for a very specific kind of problem. And again, develop first you develop a little language that lets people describe instances of the problem the chip is designed to solve. Okay, again, I always think of it as matrix multiplication as an example. It's the chip is great at matrix multiplication, but you don't know whether the matrix is sparse or dense, and what its aspect ratio is, and so on. So you but basically you compile a very specific language into a very specific chip, and that's I think that's interesting both from the point of view of the chip designer and the point of view of the compiler writer.
Jeffrey, we have 3 questions more. It's okay?
Yes.
Yes, okay. Now, David Martinez, please.
Hello, can you hear me?
I can indeed, yes.
Thank you, Professor Ullman. I wanted to ask you, how did you become interested in education and how has it impacted your life? Like, how did you manage to combine both your career development and being a professor at Stanford and other universities?
Well, being a professor is one of the ways to develop a career. I get, again, the world has changed so much. When I graduated, got my doctorate, assistant professors were the scum of the earth. Your job as an assistant professor was really not a pleasant one. You were given all the dumb committee assignments and basically had a find your own way. And so I decided I was not going to be an assistant professor. And so I applied only to industrial positions, and I was fortunate enough to get a job at Bell Laboratories, which, by the way, had a unique situation in that U.S. government law required AT&T to spend 1% of its revenue on not profit, but all revenue. 1% had to go into research. So they had, the Bell Labs basically had a built-in budget. Nobody could take it away from them. And there were more things to do than they knew. There's more money to spend than they knew what to do with it. So basically you could just go there and just pretty much do anything you wanted. I guess I always sort of viewed myself as an academic, and as soon as I was able to get an associate professorship, I left. I left the industrial research end. I mean, my first book actually was published at Bell Labs. They were happy to let me just behave like an academic anyway. I probably could have stayed there I couldn't have stayed there all my life because eventually the whole thing collapsed. But anyway, there was at least in the early days, being an academic was quite easy. There was the National Science Foundation in the United States was happy to throw money at computer scientists because there weren't that many of us teaching it. I mean, I remember the first time I put in a research proposal to the NSF, I got a call a couple of months later saying, we like your proposal, but there's one problem with it. Okay, and the problem was you asked for money to support 2 students. We would like you to support 4. So would you just send in a new proposal with a higher budget? Okay, that doesn't happen anymore. Let me trust me. But again, when I was developing my career, things were remarkably easy compared with what it is today. Now that of course doesn't help it doesn't answer your question, or at least it doesn't give you any practical advice. I mean, I would say this. First of all, if you're an administrator at a university, do your best to help the young people develop their careers, because it's not easy these days. If you're a young person starting out, what can I tell you? Try to pick a field where you are likely to have impact, because those will tend to be the fields that people want to throw money at, and also the fields that the students will want to work in. But I don't know. It's tough today. Again, I'm sorry, this doesn't really help you much, does it?
Okay, thank you. Well, now Edgar Cobantes Osuna, please.
Okay, can you hear me?
Yes, I can.
Okay, perfect. Thank you, Professor Ullman, for your talk. I think my question is more related to, well, I think I'm the same as Guillermo. I basically have most of your books and I use them to teach the subjects most of the time, theory and data structures. And my question is related to that. Nowadays, students are more interested in practicing learning languages, programming, machine learning models, and things like that. And I have seen a huge problem trying to teach foundations like complexity theory and things like that. I would like to know your opinion. And right now, at this moment, how can we make students interested in the foundations of computer science? Because at the end of the course, I always make a little form like, okay, what do you think about the course, the topics? And they always said, I'm not quite sure how I'm gonna use these topics because I want to be a web developer, engineer, and things like that. And most of the times I spend most of my time trying to look examples of how foundations are the building blocks of everything that comes in the future in their careers. I would like to know your point of view related to teaching theory now.
Yeah. Okay. Well, I would say, hold the course in the sense that the theory is still important. Understanding what computational complexity means, what NP-completeness means, and so on. I still think everyone should know that. I mean, you could probably, again, I don't know what kinds of examples you use in your class, but, okay, if someone wants to be a web developer, I don't know, can you find some, some examples, that, that a web developer might be interested in? I'm trying to think what.
Well, maybe a shopping cart is basically a deterministic automaton where you can go from one state to another depending on the interactions that you have in the web page. That's the kind of ideas I'm trying to give the students. You cannot go to another state before you fulfill certain criterions and so on and so on. But finding basically examples for everyone is being a challenge.
Yeah, it is. See, the problem with, yes, you can say, just because you say, that the processes, basically the programs that a web developer is going to write could be simulated by a finite automaton.
Yeah.
It doesn't mean that knowing about finite automata is useful in the writing of that program.
Yes.
I would say, for example, a more likely application would be for you take some simple protocol, you're trying to communicate. We're trying to set up a communication between two sources, and they want to, maybe they need to know what data transmission protocols each system is using, or something like that. And you model that as a finite automaton, and you can ask. So you can then phrase an important question of like, will this ever converge? Can be phrased as a problem in finite automata. Okay, so maybe something like that would be helpful. I'm always, I'm almost tempted to say, well, just require the course and don't, because I mean, I do think that people are better off for knowing this kind of thing. But for example, look, the mathematics department I think probably always have had the same kind of problem. What good is learning integral calculus? And what some math departments do is they will have specialized courses where the basic ideas of calculus are applied in one way or another. It's either you can apply it in physics problems, or you can apply it in economics problems, depending upon what your students are interested in. So you'll have a calculus for economists and a calculus for physics kind of a thing. But I'd hesitate to say we should have a introduction to data structures for future web developers, because those future web developers may not be web developers. They may turn out, in fact, to be doing something very different. And then by the time they graduate, there may not be such a thing as a web developer. I don't know. So it's, I still have faith that a sensibly taught theory will be good no matter what students become. And again, remember, most of your students 20 years from now will be in jobs that we don't even have names for today. So yeah, you have to think carefully about what you're going to teach them. You can't predict what's going to be important. We'll find out if I'm going to be important 20 years from now. I don't know. My instinct tells me that yes, they're fundamental enough that many people, not all of them, will use them. Somehow they'll figure into many jobs. Now, obviously not. Again, most people, most of your students will never use any. Well, sorry. Let me phrase it properly. For any given nugget that you teach your students, the vast majority of them will never use that nugget. There's no way to get around that. Okay, but some of them will, and they'll need to have it, and it'll be very important. And if you pick the nuggets you teach wisely, they learn something just about thinking that will be useful in some context, again, that we cannot imagine. Some problem that we cannot imagine people facing today, because we just don't do that today. I'm sorry, am I vague enough on this? I guess. Yeah, it's hard. It's hard often hard to motivate, but you got to try, and you got to keep teaching the theory.
Thank you. The last question is Daniel Arguedas, please.
Hello, Dr. Ullman. Thank you very much for the presentation. My question is in regards to machine learning and AI. Is there an inherent limit to where we can reach with human understandable models, or with enough development, will they ever be comparable to non-understandable models?
Yeah, that's a very good problem, and I mean, it's a very good question, and it's it's I think something that machine learning researchers are looking at very carefully. I mean, I've seen, for example, work in taking one of these. It's a million parameter neural net that's been developed by some mechanism or other, and now you've installed it, let's say, to let's say decide on your insurance premium. It's been designed in a way that's not understandable, but that doesn't mean you can't do, for example, some experiments that will help you understand it. So, for example, in again, assuming it's an insurance rating algorithm, I would, I'll put in some hypothetical person and see how much their premium should be, and then I'll change one little bit of not a bit, the technical says, but a little piece of the description of this person. Instead of living where they live, I'll move them a block away, and I'll see how the premium changes. And then I'll move them another block away, and I'll see how it changes. And I get some understanding of the system. And so I've seen people working in that way, not to build understandable systems in the first place, but to then learn how to, well, basically investigate their behavior in a way that lets you, for example, produce something that looks like association rules that says moving, for each 100 meters you move to the north, you're from this in this area, let's say, if you move for every 100 meters you move to the north, your premium goes up by 10 cents, something like that. So you can come to understand what the system is doing rather than building an understandable system in the first place. Again, so the answer to your question directly is, I'm not convinced that there is necessarily an understandability, a trade-off between understandability and the power or accuracy of the system, but at least there is some hope that understandability can be achieved, if you want to, by other mechanisms than the algorithm that implements the model in the first place. And I hope that makes some sense.
Well, that was the last question. Dr. Ullman, thank you a lot for your time. We appreciate it a lot. And Rafael Lavalos.
Okay. For the next semester, we have planned with Barbara Liskop and Donald Nutt being the next SWIT conferences. Thank you, Dr. Jeffrey Ullman. Thank you, Ariadna, and thank you, everybody, for being with us.
Well,
Hasta luego.
Yes, thank you all for listening. I enjoyed very much some very interesting questions, and I hope we had some fun. Okay.
Thank you again.
Anyway, good.
Thank you.
Bye. Adios.
Bye. Thank you, everybody.